Hi to all. So today we are going to discuss introduction to organic chemistry. So we know about organic compounds. So these are made up of carbon and hydrogens. So apart from that, if you see the proper definition for an organic chemistry, so organic chemistry is the study of chemistry of carbonic compounds. So carbon is singled out because it has a chemical diversity than unrivaled by any other chemical elements. Its diversity is based on different criteria. Suppose if the carbon atoms bond reasonably strongly with other carbon atoms bond reasonably strong with atoms of other elements. Otherwise, carbon atoms make a large number of covalent bonds. So here we are going to see a various type of structure of carbon derivatives. So where we are going to find the series of chains that has been attached covalently with each carbon atom. Okay, in general, if you see the definition of an organic chemistry, so it deals with the chemistry of a carbon, an element that forms strong chemical bonds to other carbon atoms as well as to many other elements like hydrogen, oxygen, nitrogen and other halogens. Yeah, we discussed as per the previous data. So this carbon has to make a bond with itself. That means it's a same carbon atoms, otherwise with any heteroatoms whatever it may be. Organic chemistry is a subdiscipline of chemistry that studies the structural properties, then a reaction of different organic compounds which contain carbon in covalent bond. So that means mainly this organic chemistry focus on molecules mainly composed of carbon and hydrogen along with some useful handful of other elements such as the oxygen, nitrogen, otherwise the sulfur, silicon and phosphorus. So this organic chemistry deals with the synthetic methods, then followed by reaction mechanisms and kinetics, and uses analytical methods for reaction control and purification such as chromatography methods in order to purify, otherwise in order to elucidate what the compound we have been made. So like TLC, like gas chromatography, like high performance liquid chromatography. And this structural conformation has been done by using NMR and IR, but also structure determinations such as NMR and X-ray crystallography is followed further. New field of organic chemistry, so that's going to be related for human diagnosis, that's going to show the pharmacological activity. So that's a recent trends comes under in medicinal chemistry. Apart from that, natural product chemistry, where we are going to discuss about the plant extractions. So these may be the harmful and desirable products that can be termed as drugs. So we can use it for the human elements. And material science, in industry organic chemistry used to work to discover chemistry, that means making a new molecule and process optimizing, finding better synthetic methods for large scale of production. So this is the main intention to elaborate our organic chemistry. Okay, so if you see the study of a structure determines their chemical composition and formula. A study of the properties includes its a physical and chemical properties. So then you are going to evaluate of chemical reactivity to understand their behavior. The study of organic reactions include the chemical synthesis of natural products, drugs, and polymers, and study of individual organic molecules in the laboratory. So here these organic compounds may vary in their state as solid, so in liquids or gaseous state, which contain the basic organic carbon in its molecule. So this can be given as an organic compounds. There are a large number of organic compounds and therefore a proper synthetic classification was required. Organic compounds can be broadly classified as a cyclic, acyclic, and a cyclic. Acyclic means it is an open chain in which the carbon attached by covalent bond, whereas a cyclic in which the carbon has been framed in a cyclic manner. Each and every carbon atom has been attached with a covalent bond itself. It may be saturated, unsaturated. Here we are going to see different organic compounds that have been made a framework with the carbon atoms, so and have a bond with the covalent bond with the hydrogen atoms. Yeah, we have a series of examples like methane, ethane, ethyl alcohol, ethyl chloride, and urea. So if you see these structures, each and every structure has been made a bond with a carbon. So here each and every compound we mentioned, it will have almost a saturated bond. So apart from urea, here the carbon is showing the carbonyl bond. So we'll see later on. So before going in depth, we have a outlook on carbon. So if you see the carbon, what its position in periodic table. So carbon is a chemical element with a symbol C and atomic number 6. It is a non-metallic and tetravalent, making 4 electrons available to form covalent chemical bonds. It belongs to the group of 14 of periodic table. So you are going to see the symbol there. So we are going to mention the symbol here, how the periodic table is going to show there. So we are going to draw in the sketchboard. See here. Okay, now this is the carbon. So you have the atomic number as 6, then so 12.011, so will stands for the atomic weight of the compound. So if you see the configuration, how it has been represented, they has been given as a helium in brackets, that stands for helium 1s2, then followed by here 2s2, because the configuration, excited state configuration, I am going to represent as 2p2. So this may be the ground state. If you are going to see the excited state, so before that, see here this carbon. So in periodic table, if you see in the chart, you are going to represent like this. The 6 will stands for the atomic number, 12.011 stands for atomic weight of the compound. Then here you are going to see the ground state configuration of the carbon. Then so if you are going to see any line like this, it's in a solid state, it's going to represent the character. Then after that, so they are going to show any indications like this, it will indicate it is a weakly acidic in nature. Then after that, So see here, if you go for the configuration of the compound, so in ground state we are going to see the occupation of electrons of carbon as 1s2, then followed by 2s2, then followed by 2p2. So this about the ground state electronic configuration of the carbon atom. Then now we are going to see the excited state configuration here. So if we see the excited state configuration of the carbon atom, in which you are going to retain the electrons at 1s2, then followed by here the 2s, if you are going to see the electron spin, you are going to see the transformation of these electrons to the one of the 2p orbital. So we are going to give the 2p orbital as 2px, then followed by y, then followed by z here. So in which initially at ground state you are going to see the presence of two electrons. Imagine it is present at 2px1 and 2py at one position. Now the electron at 2s subshell is going to shift towards the z. This is the excited state configuration of a carbon atom. Okay, so this has been given by Houns's rule. Electrons occupy so separate orbital rather than a pair in a 2p. Okay, now see the classification of organic compounds. We discussed about the introduction to organic chemistry. Then we have the importance of carbon. So what are the different organic compounds we have been made with the carbon, then how it has been classified. This is an important criteria here. Organic compounds has been classified mainly as an acyclic open chain compounds, then followed by cyclic compounds. So if you see the classification here, so it has been given like this. In open chain it has been divided into further two straight chain compounds, then followed by branched chain compounds. Then in case of cyclic compounds, again it has been classified as homocyclic compounds. Previous we have the word about the cyclic. If the carbon so has a bond, that means saturated bond. Okay, so it is an homocyclic. If it has so the carbon, apart from the carbon, if it have hetero atoms like nitrogen and oxygens in its cycle, so it is given as a heterocyclic compounds. So in these homocyclic compounds, again it has been classified further into alicyclic, then aromatic. So we know that so it has been given sp2 hybridized. Okay, now let's have the first one, acyclic or open chain compounds. These compounds are known as aliphatic compounds. They have branched or straight chains. We are going to see the examples. So we have the simple example, so methane, then followed by the ethane here. Then if you want to write as a butane, so we can represent the different series of structures for that. So we can give as a straight chain, then followed by so branched chain, so like isobutane. Similarly, if we are going to see acetaldehyde, a carbonyl compound, so we can represent it as an acetic acid. Both are the derivatives of a carboxylic group. Okay, acetaldehyde and acetic acid. Okay, so these are acyclic or open chain compounds. Then so if we are going to see A closed chain or a ring compounds. So what's the criteria for this? These are the cyclic compounds which contain carbon atoms connected to each other in a ring. That's why they has been given the name as homocyclics. When atoms other than carbon are also present, then it is called as heterocyclics. So here we have to go for replacing the carbon with any heteroatoms. So we are going to see the examples. So see the examples. Cyclopropane, so it's an homocyclic form. Similarly cyclohexane, so both are nothing but a saturated sp3 hybridized cyclic compounds, then followed by cyclohexaene. So here cyclohexaene will stands for an sp2 hybridized, in which you are going to see the double bond that present in a cyclic homocyclic form. So we are going to see a double bond here. Then next goes for the heterocyclic compound, in which the carbon atom is replaced with oxygen, that gives a tetrahydrofurane. So these are the examples of a closed chain. So it may be homocyclic, so otherwise it may be the heterocyclics. Then apart from that, we have aromatic compounds. So before discussing the aromatic compounds, we have to know first of all, so it has to obey the Haeckel's rule. So we'll see the later on what's the Haeckel's rule. So they are a special type of compounds which contain benzene and other ring related compounds similar to alicyclics. They can also have heteroatoms in the ring. Such compounds are called heterocyclic aromatic compounds. So that has to follow the aromatic rule. So let's have some examples here. So here we have been mentioned benzenoid aromatic compounds. So simple examples, nothing but benzene, aniline, then followed by naphthalene. Then heterocyclic aromatic compounds in which your carbon atom has been replaced with heteroatoms. Examples are furane, thiophene, and pyridine. In furane, so here you are going to see the presence of oxygen and two double bonds. Then thiophene, in place of oxygen you are going to see the presence of a sulfur, thio and phene. Then pyridine, so here pyridine, the nitrogen atom in which the benzene, one of the carbon atom, is replaced with the heteroatom nitrogen. Okay, these are about the heterocyclic aromatic compounds. We have a series of examples, so we have the separate different section for this, separate studies we have, and separate subject also it will follow. So heterocyclic chemistry, there we are going to discuss in details. Okay, next see the classification of organic compounds on the basis of functional groups. Okay, into this homologous series. So how this has been classified? So it has been classified as a functional groups, then followed by aromatic compounds, then aliphatic compounds, heterocyclic compounds, then polymers, biomolecules, then miscellaneous others. Okay, these are the classification of organic compounds on the basis of functional otherwise homologous series. Okay, so we'll see how they has been classified and what is the importance there. Let's first of all, a functional group. A functional group can have decisive influence on the chemical and physiological properties of organic compounds. We know that cell plays a very important role. Okay, molecules are classified on the basis of their functional groups. So we have, for example, so for ethane, if you are going to replace, so for example ethane, if you are going to replace, we'll see the examples there. sketchboard. For example, ethane C2H6, so this is an ethane. So now here we are going to replace one of the hydrogen atoms. So this is an ethyl here. So one of the hydrogen atom is replaced with alcohol hydroxyl group. So we are going to see different properties for ethane than to this ethyl alcohol. It's an alcoholic group. So if we are going to remove this one ethoxide ion, so it will act as a base. Okay, so we are going to see different type of physical and chemical properties by the variation of different functional groups. Okay, then now aliphatic compounds. The aliphatic hydrocarbons are subdivided into three groups of homologous series according to their state of saturation. Alkanes, so these are in general said to be as paraffins. Then aliphatic hydrocarbons without any double or triple bond. This means that just if you are going to see that bond present in between the two carbon atoms, otherwise it has to be shared with hydrogen. So it may be the single bond, it has to possess the single bond. Then alkenes here, so these are said to be alphenes, aliphatic hydrocarbons which contain one or more double bonds. This means dialphenes, dienes or polyalphenes. Next, alkynes. Here your aliphatic alkynes, so these can be given as acetylenes due to the presence of a triple bond here. Aliphatic hydrocarbons which have one or more double bonds. Then if you see a note here, both saturated alicyclic compounds and unsaturated compounds exist as a cyclic derivatives. So here, so if you see how they has been made, so if the carbon has been made up with a single bond, so here we can set it as an alkanes. Then if your carbon it's made up of a double bond, it's an alkene, alphenes. Here you are going to see the presence of a pi bond additionally. Then if the carbon is made up of three double bonds, so it is an alkynes or acetylenes. So these are about the aliphatic compounds. Okay,